Hello all and welcome to our third video in our probability series as we look at conditional probability. Now, what is conditional probability? Well, conditional probability is the probability of an event occurring given another event has preceded it. We can think of this other event as the condition, okay? Or also you could think of it as a restriction, okay? We are restricting the series of events that have occurred to, we're telling you that this other event has occurred. Okay, this event has occurred, or this condition is true, or this restriction is true. So generally the way to think of it is that it is restricting your sample space. So instead of being, so for example, what's the probability of rolling a 4 given you have rolled an even number? Well, for a dice, instead of your sample space being 1, 2, 3, 4, 5, 6, because you are now saying the condition is there was an even number has occurred, well, you've restricted it down to 2, 4, and 6. So this conditional probability, I think a great way to think of it is restricting, because it restricts your sample space. So another example there is rolling 5, given you know the number is already bigger than 3, flipping a coin twice and getting 2 tails, given the first flip produced a tail. So there's some real life examples of a conditional probability statement. Now, the rule is as follows here, or the formula that we can use to calculate it. And this line here means given. Okay, so find the probability that A occurs given B has occurred. Okay, so this second one that's what this statement is saying, is find the probability of the first letter given the second one has already occurred, and you can find that by finding the intersection of them, probability of A intersect B, divide by the probability of B. Let's have a think about why this formula is the way it is. And we can do that, I think, probably graphically is the best way to look at it. And again, thinking, given B has occurred, that means we're restricting. We know B has to have occurred. So think in terms of restricting a sample space. So let's look at a Venn diagram. So we want to find the probability that A has occurred given B. Okay, well, we need A, so we need A to occur. That's what we want. If we think in terms of winning, probability gambling or something, we want A, so any of those A's will work, but we have reduced our sample space to B because we know B has already occurred, so we have to actually reduce it to this. So what are the elements that actually give us a win, or what's the probability of A given B? Well, that section in there is essentially our win section, yeah, in there, but we've reduced our sample space to those items that are in B. So the probability of something occurring is equal to the number of ways that we can win divided by the total options. Yeah, if we think of that really clunky but intuitive idea of probability is the probability of winning is the number of ways we can win divided by the total options. Well, in this case, we can see, because we've reduced the sample space, the only options that are going to give us a win are in this section. All of these ones out here, while they do have probability of A, they aren't inside B. And we know B has to have occurred. So the number of ones that we can win is the probability of A intersect B. And what are our total options? Well, we're told B has to have occurred. So that is our total options, is the amount of people, or technically we could do N here. That would actually make a little bit more sense. Number of things inside A intersect B divided by the number of things inside B, because we've said B has to have occurred. That's the condition, so that's restricted our sample space down to our total options. Same if we look at a two-way table. Again, we are finding the probability of A given B has occurred. Well, B has to have occurred, so all of this is scrapped. That's our restriction. We've reduced down our sample space, so to actually get the win though, we want A, so that means this. So this is our winning section. That's our win out of that would be n of b in there. Okay, so same way is whenever you see conditional probability, is think of it in terms of restriction of reducing your sample space. So let's get into some problems. Find the probability of A. Well, the Venn diagram on the side, well, we need to find the total amount of items. 28 and 21. Oh, let's just do this properly. 1, 4 is 5, plus 7 is 12, plus 8 is 20. 2, 4, 6, 8, 9. So total out of 90. Now A has 21 and 14, so that is going to be 35 on 90, which we could simplify, but I'm just going to leave it as that for now, for brevity of the video. A intersect B, well, that's the intersection there. That is 14 out of 90. So what is the probability of A given B? Well, that's going to be equal to the probability of A intersect B. So, and the way to remember the formula for conditions is it's the same two letters with intersect divided by the probability of the second letter. So always the second letter because that's our new sample space. Goes at the bottom. So we said the probability was 14 over 90 is the intersect divided by the probability of B. If we actually look at probability of B, that is 14 plus 27, 37, 41. So probability of B is 41 out of 90. Now how do we do 14 divided by 90 out of 41 divided by 90? Well, it's division of a fraction, so how do we divide by a fraction? Well, we actually flip the second fraction. So in effect, we multiply by the reciprocal over 41. So the 90 and 90 cancel, so we get 14 out of 41. So that's using the formula. Let's also look at that quickly if we looked graphically using the actual Venn diagram. So we want to find the probability of A given B. So there's our reduced sample space. So we have to be in that. So none of that counts. So now we know that our total options that we have is 14 plus 27, which is 41. That's our total options. Now how do we win? Well, we want A. Well, the only thing that's left that's A is in, was in that zone there is the 14. So we get 14 out of 41. So thinking graphically about the problem versus formula, we get the same answer. Find the probability of B given A has occurred. So that's going to be equal to the probability of B intersect A divided by A is our second one. So that's probability of A. It's going to be 14 on 90 divided by probability of A is 35 on 90. So we get 14 on 90 times by the second fraction flipped. So we're multiplying by the reciprocal, so we get 14 out of 35. And same thing, okay? We could do it graphically. Probability of B given A, so we know A has to occur, so that's our new restriction. None of that has happened. And then to get a win, we need to be in B, so we get that, which is the 14 out of possible total of 35. So same answer. Cool. Let's have a go at this problem. A school of 26 fish are kept in a tank to monitor their health. They are chosen one by one to undergo a closer inspection. Of these fish, 9 have a blue tail, 12 have a white tail, and 7 have both blue and white in their tail. And this is I've done this on purpose because this can happen in the Year 12 exam where they create terrible names. So let A represent that fish has a blue tail, so A is equal to blue, and let B be the event it has a white tail. So B, even though we've got blue over here, B is equal to white. Okay, so we need to make sure we get represent this information in a Carnot map or a two-way table. So we're just doing a probability table. Okay, so we're going to go A and A dash, B and B dash. Okay, so A is technically blue. So of these, fish 9 have a blue tail. So there's going to be 9 there. There's 26 total. Okay. 12 have a white tail, so B is white, so that's going to be 12 over there. And 7 have both blue and white in their table, so we're going to put 7 in there. So that means that needs to be, let's put it in different color ones that we then calculate. So that needs to be 2, that needs to be 5, 9 to 26 is... Come on, work brain. 17, yes. Okay, 12 up to 26, that needs to be 14. That means that needs to be 12, and that all adds up and works both ways. Cool. Find the probability that a fish with a blue tail is chosen. So probability blue is A. So probability blue would be 9 out of 26. And we'll just leave it again. That normally would simplify, but for sake of brevity, find the probability that a fish with a white tail is chosen, given it also has blue in its table. So we want to find the probability that white, so white is B, so we need to win, we need white is chosen, given it has blue in its table. So given that it is A. Okay, so that is going to be equal to the probability of B intersect A divided by probability of second letter, which is A. Okay, so B intersect A is going to be 7 out of the 26, that's there, divide by probability of just A, which was 9 out of the 26, so that turns into 7 over 26 times by 26 on 9 is 7 out of 9. Cool. And same thing, we could show this graphically, okay? Finding the probability of B given A. So that means we're restricting our sample space to just A. So effectively none of that matters. We've restricted just A, but we actually want B to win. So there we go. So we need those 7 that have the B out of the total possible 9, which is 7 out of 9. So same thing, you can see it graphically on a two-way table, just like you can on a Venn diagram. And gives the same answer as the formula. Right, and this, if there's one thing out of this whole topic that you need to make sure you get out of this whole chapter is conditional probability, because it is always in year 12, methods. And for example, here's 2017 exam question 15 from the year 12 exam methods. So a group of 50 students were surveyed to see whether those studied accounting and biology, and we've got this following information. So A is for accounting, A dash not, B for biology, B dash not. Total of 50 students were surveyed. 14 of these students were found to study both, so we can put 14 in for both. The other findings are summarized using set notation. N of A is equal to 20, so the number of students total that studied accounting is 20. And N of not A intersect B is 18, so not A intersect B, so that needs there. Okay, not A intersect B needed to be 18. Okay, so from that we can now fill in the rest of it. So that needs to be 6 to add up to 20, 20 to get to 15, that needs to be 30, so that needs to be 12. 6 and 12 is 18, 14 and 18 is 32. And that works adding that way as well. Yeah, that all works. Cool. How many students study biology? So that's effectively asking N of B is 32. How many students do not study accounting and biology? So that is N of A intersect B. I need to not study both. That is that one there, so that is equal to 12. Cool. Calculate the probability of A dash union B dash. So that is equal to, using the addition rule, because unions we can't read off a two-way table or a Venn diagram. So that's the probability of A dash plus the probability of whatever the second one is, which is B dash, take away the intersection of them, A dash, B dash. So probability of A dash is 30 out of 50 plus probability of B dash is 18 out of 50. Take away the intersection of them, A dash, B dash is the 12 out of 50. So that is going to be equal 30 plus the 18, 48, take 12 is 36. Yeah, 36 out of 50. And again, you could simplify. Calculate probability of A intersect B dash. Okay, that's pretty easy. Probability of A intersect B dash. So we want A intersect B dash. So that's that there. That's 6 out of 50. So that is equal to 6 out of 50. Okay. Calculate probability A union B dash. So again, it's a union. So we're going to need to do a addition rule. So we're going to get A plus probability of B dash, take away probability of A intersect B dash. Probability of A, 20 out of 50, plus probability of B dash, we know that from a previous question was 18 out of 50, take away A intersect B dash. A intersect B dash. 6 out of 50. Okay. 20 plus 18, 38, take away 6, so that's going to be 32 out of 50. Cool. Okay. Show that the event A and B are not mutually exclusive. So what is a reminder of what mutually exclusive is? Mutually exclusive means the two events have no overlap. So if they look like a Venn diagram, they would look like that. They have absolutely no values in common. There's no people in one set that are in both sets. So since n of A intersect B in our case, so we want to have a look at an overlap, and in our case, our overlap, A intersect B, is equal to 14, does not equal to 0. So there is some overlap. Therefore, they are not mutually exclusive, because we just said that there is overlap, but to be mutually exclusive they can't be. Okay, and finally we now get to use conditional probability. Find the probability of A given B has occurred. So that is going to be equal to the probability of A intersect B divided by the probability of the second letter. So A intersect B is 14 divided by 50, divided by probability of B. Probability of B is 32. 32 out of 50 is equal to 14 on 50 times by 50 on 32. Gives me 14 on 32. And again, you'd simplify. That's our basic uses of conditional probability. One handy thing with the conditional probability rule is that you can rearrange it. Okay, you can actually rearrange it to get intersect by itself. Okay, and once it's rearranged like this is technically called the multiplication rule of probability. I never remember it written this way. I just know that you can rearrange this. Okay, so if we've got divided by probability of B, we can times by probability of B to that side, times by probability of B to that side, and now you have the formula written as the multiplication rule. And we can use this sometimes when we might need to find the intersect given we're given some conditional information, which can happen, and especially because it's sort of hard to write this conditional information in a two-way table. So, really quickly, let's have a go. And we'll just do this example. You won't worry about the full tree diagram stuff. Okay. At an ice cream shop, 35% of the customers are adults, while the other 65% are children. It is known that 20% of adults like the flavour double chocolate fudge, while 15% of the children prefer the while 15% of children prefer double chocolate fudge flavour. Okay, so let's give some notation. Okay, so we're going to say adult, A is equal to a person being an adult, C is a person being a child, okay, and we will go F for they like the double choc fudge. Okay. So now we have that, we can now write some of this information in a in probability notation. So an ice cream shop, 35% of the customers are adults. So the probability of them being an adult is 0.35. Probability of a child is 0.65. Okay. And then we get to this bit here. How can we write that? Okay. So it is known 20% of the adults like the flavour. Okay, so we're restricting our group to adults. Okay. So the probability that they like the fudge, given they are an adult, is equal to 0.2. That's how we can write out that information there. It's known 20% of adults, so since we've got of adults, that's our restriction. We're restricting our sample space. Of those adults, then 20% of them like chocolate fudge. And same with this last bit, while 15% of the children, so of the children is our restriction. So we've restricted to children, and they also like the fudge, is 0.15. Cool? So, find the probability that a customer chosen at random prefers double choc fudge and is a child. So we want to find the probability that they like the fudge and, okay, so and means we need an intersect. We also need them to be a child. It's not it's not a conditional one, so we need to find this. So we're asked to find an intersect, and we've got some conditions, so we can then use this multiplication rule. We're asked to find this, so we need the conditional times by probability of the second one. So this is actually going to be equal to the probability given they're a child times by the probability they are a child. So we have that information, that is 0.15 times by probability that they are a child is 0.65. And use our calculator. 0.15 times by 0.65 is 0.0975, which if we want to write as percentage is 9.75%. So pretty low. Part B, a customer chosen at random prefers double chocolate fudge and is an adult. Okay, so we're asked to find the probability that they like fudge and that they are an adult. So that is equal to the probability that they like fudge given they are an adult times by the probability that they are an adult, which sort of makes sense. What's the probability they like fudge if they are an adult times by what's the probability that they are an adult? Okay. So fudge 0.2 times by probability now it's 0.35. 0.2 times by 0.35 is 0.07, which is equal to 7%. Okay. And that's it. That's all we're going to do for this video. Like I said, partway through, if there's one thing that you take from this whole topic, it's this section. If you have any questions, as always, ask in the comments below on Google Classroom or shoot me an email. Thanks and see you.